Hello and welcome to this FP3 exam paper walkthrough. This was the October 2021 paper. You were allowed a calculator and the formula booklet. Question number 1. The curve C has equation this from 7/2 to 13. Using calculus, determine the exact length of the curve C, giving your answer in this form where P and Q are constants to be found. The length of a curve formula is given in the formula booklet. Here it is. So we're going to need to differentiate our equation, half r cosh 2x, back to the formula booklet. In the FP3 section for differentiation, here it is. So that's the derivative of r cosh x, but we've got a half r cosh 2x. So we're putting in 2x, and that squares up to give us 4x squared minus 1, and we've got a half in front. But then we need to multiply it by the derivative of the function inside, which is a 2. So that cancels out, and we get 1 over the square root of 4x squared minus 1. This is dy by dx, and now we want to square it. 1 over 4x squared minus 1, and then we want to add 1 to this. To put these two together, I'm going to change that into the same denominator. And then these two cancel out, and we get 4x squared over 4x squared minus 1. Now for the formula, we need to square root that and integrate. So the integral becomes the square root of 4x squared over 4x squared minus 1, and we can do top and bottom separately here. So that becomes the integral of 2x over the square root of 4x squared minus 1 dx. Now part of me wants to play around with the 2x's to try and get those to cancel out, but I don't want a 1 divided by 4x squared here. Instead, I'm going to write that square root in index form here in the numerator as this. Now to integrate this, I recognize that 2x is the derivative, or close to the derivative, of 4x squared minus 1. The key point being, when you differentiate 4x squared minus 1, you get an x. It's an 8x instead of a 2x, but it's close enough for what we need to do next, which is to consider what would happen if we differentiated this bracket with a power higher, like this. And if I were to do that, the half would come down the front. We get 4x squared minus 1 to the minus a half times by the derivative of the function inside the brackets, which is 8x. That would cancel and give me 4x squared minus 1 to the minus a half, which is very close to what we're trying to integrate. It's 2 times bigger, so if I put a half in front of all of this, it will equal the thing we're trying to integrate here. So we can integrate directly to give a half 4x squared minus 1 to the power of a half. Then we need a plus c unless we've got limits, which we do, 7/2 to 13. And this has come from this integral here. That gives me a half 4 times 13 squared minus 1 square rooted minus a half 4 times 7/2 squared minus 1 square rooted. Putting that on my calculator, I get 15/2 root 3 minus 2 root 3, which is 11/2 square root of 3. That's the end of question number 1. On to question number 2. Given that cosh y is equal to x and y is less than 0, use the definition of cosh y in terms of exponential functions to prove that this is true. So we can't just go to r cosh and the formula booklet, we need to use the definitions of cosh y, so that's e to the y plus e to the minus y over 2 is equal to x, and now we're trying to solve this equation. So bring the 2 over, e to the y plus e to the minus y, multiply the whole thing by e to the y, and that will give us a quadratic in e to the y. This becomes e to the 2y, or e to the y squared. This becomes a 1, and this becomes 2x e to the y. Bringing that term over here on the left, minus 2x e to the y plus 1 equals 0, and then we can apply the quadratic formula. X equals is what I would normally write, but here the x in that sense is e to the y, and that equals minus b, which is 2x, plus or minus the square root of b squared, so that's 4x squared, minus 4 times a times c, all divided by 2 lots of a. So a bit of rearranging here first, a bit of simplifying. 2x plus or minus the root of 4x squared minus 4, so I can factorize out that 4 and have 4 lots of x squared minus 1, which is great because we can split that square root in a moment. That gives us 2x plus or minus the root of 4, 2, times the root of x squared minus 1, all over 2, so both of these cancel with this, or you can factorize them out first, and we get x plus or minus the square root of x squared minus 1, and that's e to the y. But what we want is y, not e to the y, and we want a log, but we've only got this negative here, not a plus and a minus. And it's a little bit tricky to get this final mark because you need to justify getting rid of this plus and only having the negative symbol. And the way we do that is we know that this thing must be greater than 0. You can't get a negative answer out of e to the power of something. But given that y is less than 0, not in general, but in this case, in this question, y must be less than 0. If a power is less than 0, that means e to that power is less than 1. And that's because y is less than 0. But we also know that x must be greater than 1, because if x is less than 1, then this thing here is going to give us a negative number inside the square root if it's between sort of minus 1 and 1, or if it's less than negative 1, in which case this part is okay, we're going to get this whole thing here less than 0 if x is less than negative 1. So all of that thinking tells us that x must be greater than 1. The magnitude must be greater than 1 because of the square root, and it can't be less than negative 1 because that would give us something less than 0 overall, which can't be true for e to the power something. So this statement and this statement both go together to mean that your plus cannot give you a solution. If you have a plus there and x is greater than 1, you will always end up with an answer greater than 1 out of this. Therefore, when we take logs, y is equal to log of x minus the square root of x squared minus 1. Now, I would imagine a lot of people would not get that final mark. I certainly wouldn't feel bad if you missed it first time through. But that is our final answer for 2. On to question number 3. Here we've been given the equation of ellipse E. The line L is the normal to E at the point P. Using calculus, show that an equation for L is this. So we're using this point P, 8 cos theta, 6 sine theta. Take note it's the normal, not the tangent. And our equation is x squared over 64 plus y squared over 36 equals 1. And this should be a fairly standard method by the time you get to the exam. We differentiate, whichever method you prefer. I tend to go with implicit differentiation. dy by dx is equal to 0. Rearrange, dy by dx is equal to minus x over 32, cancelling that. And then we have an 18 coming up and a y going down. Not the neatest way of writing it. That gives us minus 9x over 16y. Now at p, the gradient becomes minus 9 times 8 cos theta over 16 times 6 sine theta. That cancels there, that cancels there, and that gives minus 3 cos theta over 4 sine of theta, but that's the tangent, so call that m1, m2, the normal, 4 sine theta over 3 cos theta. put that into our normal line equation. Y minus y1 is equal to mx minus x1 using p, and we get y minus 6 sine theta is equal to m 4 sine theta over 3 cos theta times x minus x1, which was 8 cos theta. Now we want to make it look like this, combining the sine theta cos theta on one side, and the x was positive there, so we've got 4x sine theta minus 32 cos theta sine theta. And what I should have said first is I'm multiplying across the 3 cos theta, 3y cos theta minus 18 cos theta sine theta. So we want the 4x to be positive, even though I'm going to write it on the left. That makes the 3y negative, and 32 minus 18 is 14 cos theta sine theta as required. So that's part A finished. The line L, that's the one we've just shown, meets the x-axis at the point A. So A happens when y is equal to 0, and meets the y-axis at point B. So that's when x is equal to 0. The point M is the midpoint of AB. Determine a Cartesian equation for the locus of M as theta varies, giving our answer in this form, where A, B, and C are integers. So we've got L from part A. I just put in y equals 0 to find the point A, and x equals 0 to find the point B. For point A, y equals 0. Putting that in gives us 4x sine theta equals 14 cos theta sine theta. So x is equal to 7 over 2 cos theta. For point B, x equals 0, put that in instead, and that gives us minus 3y cos theta is equal to 14 cos theta sine theta. So y is equal to minus 14 over 3 sine theta. So this is A, 7 over 2 cos theta 0, and this is B, 0 minus 14 over 3 sine theta, and then M, the midpoint, is the average of x and the average of y. But because we've got a 0 here, the average of that, add them together, divide by 2, just divides this by 2. Same for the y coordinate, because of the 0 on top here, we just divide that by 2. Now we do our usual trick of letting the x coordinate equal capital X. Do capital X just to show it's different from the previous x's that we've used. Capital Y, 7 over 3 sine theta. And then we need to combine these into a single equation without theta. So we square them both. That gives 49 over 16 cos squared theta, which is the key point. And over here, 49 over 9 sine squared theta. So we can rearrange both of these and substitute them into the identity sine squared theta plus cos squared theta must equal 1. Sine squared theta is equal to 9y squared over 49. Cos squared is 16x squared over 49. So multiply everything by 49 and we have our final answer, where each of those are integers. Just check that we've finished. Part B finished, yes. On to question number 4. Here we've got a matrix M. Show that determinant of M is equal to 5k minus 10. So here's our determinant, and we do the first element 2 times by its minor, 3 times k minus 2 times 1, minus 0 times by its minor, k times k minus 2 times minus 2, and then plus minus 1 times its minor, k times 1 minus 3 times minus 2. This gives us 6k minus 4 minus 0 minus k minus 6, and that is 5k minus 10. That matches what we've been given. And then they say, given that k is not equal to 2, that's because that would make this determinant a 0, and there would be no inverse. So given that that's not true, there is an inverse, find the inverse in terms of k. So for the inverse matrix, we want the matrix of minors, and we've already got 3 of them here. So that's 3k minus 2, k squared plus 4, k plus 6. Continuing on, we've got 0 times k minus 1 times 1. The middle one is 2 times k minus 1 times minus 2, 2 times 1 minus 0 times minus 2. Final row, 0 times 2 minus 1 times 3. 2 times 2 minus 1 times k, and finally 2 times 3 minus 0 times k. There's our minors. Now we need to apply the cofactors pattern, which is this. So C is equal to almost the same thing with some key differences. This becomes a negative. This becomes a negative. So does this. And so does this. Then we've got our transpose matrix, where we take all of the rows and turn them into columns. So the first row becomes the column here. The second row becomes the column here. And the third row becomes the column here. Then to get the inverse matrix, we do 1 divided by the determinant, which we found was 5k minus 10. And then we rewrite the transpose matrix like this. And that is the inverse matrix. That was part B, but there is a part C. The points given, O, A, B, C, are the vertices of a tetrahedron T. The transformation represented by matrix M transforms T to a tetrahedron with volume 50. Determine the possible values of K. So here we're using the fact that volume 1 times by the determinant of M, or really I should say the magnitude of that, especially because we've got a plural here, that's where we're going to get 2 answers. That is equal to volume 2, and we're being told that it transforms T to a tetrahedron of 50, so volume 2 is the 50. We know the determinant of M is 5k minus 10. We need to find volume 1. To find the volume of a tetrahedron, that's 1/6 of the scalar triple product A cross B dot C. And because one of the points of our tetrahedron is very kindly the origin, we can use all of these 3 sets of numbers for our vectors. So I'll take all that information down here and put in the vectors. So we've got 1/6 the magnitude of A, 4 minus 8, 3, cross B, minus 2, 5, minus 4. It doesn't really matter what order you do these in. 4 minus 6, 8. That gives us a cross product of minus 8 times minus 4, minus 5 times 3, 3 times minus 2, minus 4 times 4, and 4 times 5, minus 8 times minus 2, still dotted with this. So that simplifies to 17, 10, 4. 17 times 4 is 68 minus 60 plus 32. That gives us 40 over 6, or 20 over 3. So this is volume 1. And then we had volume 1 times the determinant of M is equal to 50. So 20 over 3 times by 5k minus 10 is equal to 50. But there's no guarantee it is 5k minus 10 that will give us the positive. It might be that that gives us a negative that we would have to turn positive for this process. So our 2 possibilities are 5k minus 10 or minus 5k minus 10, i.e. 10 minus 5k. That's 15 over 2, obviously for both of these. Over here, that gives us k is equal to 35 over 2 over 5 is 7 over 2. Over here, our 5k is equal to 5 over 2, so k is equal to a half. So these are our two possible answers, a half or 7 over 2. That, I think, was the end. Yep. Two values. On to question number 5. The skew lines L1 and L2 have equations here. I'm going to change those. I just prefer column vectors. Where lambda and mu are scalar parameters, determine a vector that is perpendicular to both L1 and L2. Perpendicular to both means we are going to do the cross product of their two direction vectors. So direction vector number 1, 5, 1, 0, cross that with 8, minus 2, 3, and that gives us a vector direction that is perpendicular to these two vectors. That's 3 minus 0, 0 minus 15, and minus 10 minus 8. 3 minus 15 minus 18, or because it's just a direction, we can divide that by minus 3 and get minus 1, 5, and 6, just in case we're going to continue using it. And we are, because it says determine an equation of the plane parallel to L1 that contains L2. So the two lines aren't in the plane together, but because the plane is parallel to L1, then the direction of that line is still a direction that is in the plane. So that might seem a bit weird. But we can still use this answer from A as our normal to the plane. But we've got to do this in two ways. We want the form R equals A plus SB plus TC, and actually that's much easier given what we've been given in the question and what I've just said about the two directions. These are the two directions of the two lines, the ones that we've used in part A. And we're being told that L2 is in the plane, so the point on L2, this one here, is a point on the plane. And that can be this A here. So we're using 3 of the 4 vectors that we've been given. So B part I is surprisingly straightforward. We take the point from L2, that's 2 minus 4, 4. The direction from L2, 8 minus 2, 3. And the direction from L1, 5, 1, 0. And that's it. And that's why it's only worth 1 mark, I guess. In part 2, in the form r.n equals p, we've done part of the work by recognizing that this is the normal. And again, we know the point in the plane is the same point as in line 2. So if we do part 2 here, r.n is equal to a.n, using a as we've done in the one just above it, 2 minus 4, 4, and then the n from part A, minus 1, 5, 6, r dot minus 1, 5, 6, and then we just need to work out this dot product. Minus 2 minus 20 plus 24, and that gives us a 2. And there's our second plane equation. Part C, determine the shortest distance between L1 and L2, give your answer in simplest form. Now because these lines are skew, that means, if I keep this going a little bit, it's hard to draw these in 3 dimensions, but the normal to the plane is actually also the direction of the line of shortest distance, i.e. the perpendicular between the two, because that's what the normal was, that's how we worked it out, perpendicular to both lines. Now if we can get another line connecting them, which we can, because we've got a point on each of them, this line here is using this point that we've used already, and this point, and then we can use the idea of projection, and this is given in the formula booklet, that if you project A in the direction of B, the distance there is equal to this. So if I use the same notation that I used in a video, call this A with a direction vector B, call this C with a direction vector D, then this is B cross D, the thing we worked out here, And then c minus a, or a minus c, is what we're trying to project in that direction. So this general form becomes c minus a dot b cross d divided by the magnitude of b cross d. And we can turn that into n in this case, because we know that's the normal to the plane. That's most of the idea. All that's left to do is to work it through. So here's all my information, including my rather questionable drawing, and this is the key idea that I'm going to be following with. So we've got 1 point, 2 minus 4, 4, minus the other point, 1, 2 minus 5, to get this c minus a line, and then we're going to dot that with the normal, minus 1, 5, 6, and divide it all by the magnitude of the normal. I'm not going to bother drawing the big magnitude symbols, but that should all be magnitude, because obviously we can't get a negative distance, but we might get a negative answer out of this. If so, I'll just change it to positive at the end. 2 minus 1 is 1, minus 4 minus 2, 4 minus minus 5. Dot with this. This is 62. That gives me minus 1 minus 30 plus 54 over root 62, which is 23 over root 62. So the shortest distance, you can write like that, or if you don't like the square root in the denominator, you can write like that. And that was part C finished. Yes. Part C here. On to question number 6. Here we've got an integral with a rather nasty looking limit there, although this is x squared, so it might not be too bad when we get there. N is greater than or equal to 1. Prove that for n is greater than or equal to 5, this is true. Here I can see the little trick that we're going to do is to separate x to the n as x to the n minus 1 times x. And the reason we're going to do that is because of this x squared here in the cos expression. And if we differentiate cos x squared, that would give us minus sine x squared times 2x. So having the x times a trig function helps, because that's a derivative of a trig function with x squared. So I can use that idea of seeing that to think that if I've got x cos x squared, that's probably going to integrate to sine x squared, or some sort of multiple, maybe a half or 2 times sine x squared. So I hope that shows a little bit of how I was thinking as I saw that expression as to why I've split this like this. Now we can apply the integration by parts formula using this as the thing that will differentiate. So this is u and this is v prime, and integrating that, as I just said, will give us something like sine of x squared. Consider that on the side now. If we differentiate sine of x squared, that would give us cos of x squared times by 2x. So the only difference is the 2, so if we want half of that, we've got half of that there. So integrating x cos x squared, i.e. v, is a half sine of x squared like that. Differentiating u is a bit easier. We bring the n minus 1 down, and then we have x to the n minus 2. Looking at what we're trying to prove, that makes me feel confident, because we've got an n minus 1 here, and then we have an n minus 3, which immediately implies to me that we're going to do the same thing, because we're going to have this sine x squared. So if I split this x to the n minus 2 into x to the n minus 3 times x, we're going to be following that same pattern a second time. But I'm getting ahead of myself there. Let's go with what we've got for now. uv prime, the integral of that, is uv minus the integral v u prime. So in is equal to u, that's x to the n minus 1, times v, half sine of x squared. And we have limits, so we're going to need to evaluate that from 0 to the root of pi by 2 minus the integral of vu prime. So that's n minus 1 x to the n minus 2 times a half sine of x squared. So dealing with the limits here, we've got root pi by 2 to the n minus 1 times by a half, and if you put that into the sine there, we get a 1, so that's just a half. And then for the 0, we get 0 times 0. So that's our limits on the first part. And then if I take the n minus 1 out of the integral here, and we integrate, take the 2 out as well, we integrate x to the n minus 3 times x sine x squared. So we'll do the same thing again. We'll call this one u, and then when we differentiate, we get n minus 3 lots of x to the n minus 4. Call this one v prime, and then when we integrate that, because it's the same pattern as before, we get a half cos x squared, but this time it's a minus. Then we can apply the integration by parts formula. Just a word on this first term. We've got pi by 2 inside a square root. The square root is the same as a power half, so if we pull out the power half, we have n minus 1 over 2 as the power overall. So that can change into pi by 2 to the power of n minus 1 over 2, and we're timesing that by a half as well, half in front. Then we have minus n minus 1 over 2 times by uv from the integration by parts formula. U is x to the n minus 3, and v is minus a half cos x squared. Then we have minus n minus 1 over 2 again as the multiplier in front, but this time we have a minus, so that becomes a plus, integral v u prime. U prime is n minus 3 x to the n minus 4, and v is minus, so this becomes a minus again, a half cos x squared. Now we need to apply our limits on this part here, 0 root pi by 2, and tidy up the integral, and hopefully, because now we've got cos x squared and an x to the power of something, we can put it back in terms of in. It looks like in minus 4. Fortunately, this time when we put the limits in, we get 0 for cos of pi by 2, so that first term is 0, and we get 0 because of the x to the power n minus 3. So that all nicely simplifies to nothing. This is still how it was. And then here we've got minus n minus 1, n minus 3, and if we pull the half out, together with the other half that's already there, that's a quarter, and then we have integral x to the n minus 4 cos of x squared, which we can replace with in minus 4. We've got n minus 1, n minus 3 over 4, and this strange thing on the front still. But hopefully that matches what we needed. It does, except they've written a quarter and I've written divide by 4. That's good enough. So that is part A finished. Part B is to apply this for I5, n equals 5, in simplest form. So we've got a half, pi by 2, 5 minus 1 is 4, divided by 2 is 2, minus 5 minus 1, 5 minus 3, I1. Now we can't do this with I1 because that will give us I minus 3, so I need to convert this into the integral, but if it's x to the n and n is a 1, then that's x cos x squared, which we've already integrated as part of our process. So we know we can do that. So this becomes pi squared over 8, 4's cancel out there, and actually if we put that 2 inside the integral, that gives us a sine of x squared exactly, 0 root pi by 2. putting in the limits here, that gives us sine of pi by 2, which is a 1, minus sine of 0. So our final answer, pi squared over 8 minus 1 for I5. On to question number 7. Here we have a hyperbola with this equation here, so b is equal to 5, where a is a positive constant. The eccentricity of h is e. Determine an expression for e squared in terms of a. If you forget this, it's in the formula booklet, but we've got the connection b squared equals a squared e squared minus 1. We know b squared is 25, divide that through by a squared, e squared minus 1, so e squared is equal to 25 over a squared plus 1. That's part A finished. The line L is the directrix of h for which x is greater than 0. The points A and A' are the points of intersection of L with the asymptotes of h. Determine in terms of E the length of the line segment AA'. Okay, I feel like I need a diagram here. So a hyperbola comes in something kind of like that, and the directrix is, say, here, and the focus S here. The directrix is line L, and it intersects with the asymptotes. Though my diagram isn't great, it looks something like this, and that's A and A'. The conic section of the formula booklet has this information, directrices and asymptotes here. So the equation of L is x equals A over E, and the equation of the asymptote is x over A equals y over B, and we know B is 5. And this one down here, x over A is equal to negative y over B. And we need to find the intersection points A and A', so I can combine the equation of L with the equations of the two asymptotes. Take that diagram down here, and using the equation of the directrix, we can rearrange this to give x over A is equal to 1 over E, and I can substitute that in directly here. So 1 over E is equal to y over 5, or if I want to do them both at the same time, so y is equal to plus or minus 5 over E. So the positive root is A, and the negative is A', or what I've written as A1 on my diagram for some reason, A'. The distance between the two then, which is what we actually want, A to A', is two lots of the positive version. So it's 5 over E plus 5 over E, 10 over E. And that is the distance that we need for part B. Looking for part C, the point F is the focus of H for which x is less than 0. So I've got the focus written as S on my diagram, but that's x is greater than 0. So the other one, if I keep that line going, over here somewhere, there's F. Given that the area of triangle AFA', which should be symmetric about the x-axis, given that the area of that is 164 over 3, show that A is a solution of the equation given. So we already have the distance A to A', this one, so the area is equal to a half of that distance, which we know is 10 over E, times the x-coordinate of F, or the magnitude of the x-coordinate of F, which we know is minus AE from our focus point, plus the x-coordinate of the directrix to get this full distance here. So I'm adding on this distance here, which is AE, plus this little distance here, which is this, A over E. So my area, if I write it here, well I can see the diagram, is a half times 10 over E times AE plus A over E. And that has to equal 164 over 3. But what we're trying to show is a cubic in A without any e's, so we're also going to want to use this connection here. E squared equals 25 over A squared plus 1. So to do that, what I want is E squareds. So first of all, I'll cancel this, make that a 5, bring that down on the other side, 164 over 15, and then expanding this bracket, we've got A plus A over E squared. I don't really want to work in the denominator, so I'm just going to change that into this. And then have a 25 over a squared plus 1 plus a is 164 over 15. 25 over a squared plus 1. That gives me 25 over a plus a is equal to 820 over 3a squared plus 164 over 15. I'll combine those two a's into 2a and multiply everything by a squared. So here we get 25a. The two a's here become 2a cubed. This is 820 over 3, and this is 164a squared over 15. Now we need rid of that 15. 375a plus 30a cubed is equal to 4100 plus 164a squared, and then everything on the same side together gives us negative 164a squared. Positive 375 and negative 4100 equals 0. Does that match? Yes, that's looking good. Part D. Hence, using algebra and making your reasoning clear, show that the only possible value of a is 20 over 3. So because it's a cubic, I'm going to use that to help me. If a is equal to 20 over 3, then 3a minus 20 equals 0, and that's one of my factors. So part D here, we're using 3a minus 20 as one factor, and then we've got pa squared plus qa plus r as the other factor, the quadratic factor, and then I can consider the different things and what they need to make. We need minus 20 times r to make minus 4100, so r must equal 205 for this times this to equal this. 3 times p must equal 30, so p must equal 10, and then we're going to need 2 for q, so 3a times qa is 3qa squared, minus 20 times pa squared must equal minus 164a squared. We know p is 20, so that's minus 200. That gives us 36 for 3q, and q is 12. So our quadratic here is 10a squared plus 12a plus 205. And we still have the 3a minus 20. And then we need to show that this is the only solution. And to do that, we're going to show that b squared minus 4ac is negative here. That's 12 squared minus 4 times 10 times 205, which is negative 8056, very much less than 0, therefore no real roots. Therefore a equals 20 over 3 is the only solution. That's the end of question 7. On to the final question of the paper. Here we've been given y equals arc cos 2 root x, and we need to find the derivative. To do this, I'll jump across to the formula booklet. This is the one we're looking for. So knowing this, we're going to apply the chain rule. We've got minus 1 over 1 minus x squared, so that's 4x when we square that, times by the derivative of 2x to the half, which is just x to the minus a half. So I would probably write that as minus 1 over root x times by the root of 1 minus 4x. There's our derivative for part A. Part B, show that the integral of y dx is equal to this. Now because of the format integral equals not integral plus integral, that suggests to me to use the integration by parts formula. To use integration by parts on this, what we will do is consider this to be what it is, times 1. and then the 1 here will be v prime, and we can integrate that to give x, and then this will be u, and we differentiate that using what we've just found in part A. So going with that method, the integral of arc cos 2 root x times 1, if you want to make that clear, u is equal to arc cos 2 root x, so u prime is equal to part A solution, which is this. V prime is equal to 1, v is equal to x, uv, the integral of this is equal to uv minus the integral v u prime. So our integral is equal to uv, v is x, and u is arc cos 2 root x, minus the integral of v again is x, u prime is minus 1 over root x root 1 minus 4x. Put that there, and that can become a plus there. Now what are we trying to do? We're trying to show it's equal to this. We're very close. We just need to combine our x and the root x in the denominator to get this root x in the numerator. Everything else stays the same. And there is our solution for part B. Part C, use the substitution root x equals a half cos theta to show that this part, which is just this bit that we're looking at the moment, this thing here is equal to this thing on the right. I'll be honest, if we have to do a substitution, I do like it when they tell you what substitution to use. So it's root x equals a half cos theta. We're going to need dx as well in terms of theta, so I'll square everything and then differentiate. So treating that as a bracket, the 2 comes down the front, so that becomes a half. Then the power goes down by 1, and then you times by the derivative of the function, so minus sine theta. So that's minus sine theta cos theta over 2. So we know what root x is for the numerator, we know what x is to slip into this denominator here, and we know what dx is in terms of theta and d theta. So now we can go ahead and do the substitution. Root x over root 1 minus 4x dx, and we had limits on this, 0 to 1 over 8. I'll deal with those in a moment. But for now we've got root x, that's a half cos theta, divided by the square root of 1 minus 4 times x, which is a quarter cos squared theta. That's good, that'll cancel with that. And then we've got 1 minus cos squared, that's sine squared, and the square root of sine squared is sine. So I can see a lot of simplifying coming up shortly. Write that as this, and then d theta. Now for the limits. Down here we've got x equals 0, and we need to know theta. So putting in x equals 0, that gives us 0 equals a half cos theta, so 0 equals cos theta. So theta is equal to pi by 2. When x is equal to 1/8, the square root of that is root 2 over 4 equals a half cos theta, and that gives us theta equals pi by 4. That's not too bad. So we've got pi by 2, the bigger one on the bottom, pi by 4, the smaller one on the top. Again, I'll just check what it is we're actually trying to do here. Are we trying to solve it? No, we're just trying to make it look like this integral here. And that is a positive. And at the moment, we've got a negative. So I think we're going to end up switching our limits. But that's okay, we can do that. So for now, combine the halves, we get minus 1 over 4, integral from pi by 2 to pi by 4 of cos squared theta sine theta over the square root of 1 minus cos squared theta. And 1 minus cos squared theta is equal to sine squared theta. So the root of that is the root of this, and so that cancels with sine theta in the numerator. That gives us minus 1 over 4 integral pi by 2 pi by 4 cos squared theta d theta. So in order to make this positive, we need to flip our limits. So this is pi by 4, this is pi by 2 cos squared theta d theta. Now it looks like how it should, and we've got the lower limit on the bottom, a, and the bigger limit on b. Part D, hence determine the exact value of this thing here, 0 to 1 over 8 of the original function. So that is this with those two limits, and what we found in part C is just the second bit, so we need to apply those limits 0 and 1/8 onto this first section here, as well as going ahead and calculating what this is. So writing that out, part D, integral from 0, 1 over 8 of arc cos 2 root x dx is equal to x arc cos 2 root x from 0 to 1 over 8 plus 1 over 4 integral from pi by 4 to pi by 2 of cos squared theta d theta. Now to integrate cos squared theta, we're going to change cos squared theta into a half cos 2 theta plus a half using the double angle formula. So the integral is equal to 1 over 8 arc cos 2 root 1 over 8 minus 0 plus 1 quarter, the integral pi by 4 to pi by 2 of a half cos 2 theta plus a half. The first term there is pi over 4 times 1 over 8, so that's pi over 32, plus a quarter of sine 2 theta divided by 2, but there's already a half there, so that's a quarter sine 2 theta, plus theta over 2 from pi by 4 to pi by 2. Working with that, sine of 2 times pi by 2 is 0, and then pi by 2 over 2, so there's our first limit, minus sine of 2 times pi by 4 is a 1, so that's a quarter, plus pi by 8. That gives me pi by 32 plus a quarter of pi by 8 minus a quarter. Expanding that out, we get pi by 32 plus pi by 32 is pi by 16 minus 1 over 16. And that is the answer for the integral. That's also the end of the paper. I hope that has been really helpful for you.